Hello again, and welcome to the Cedille cast, a series of videos on writing programs and proofs in Cedille. In the previous video, we saw how to derive induction for imbricative lambda encodings of data types, rather than adding them to the theory as primitives. This was achieved by adding three new typing constructs to the calculus of constructions: dependent intersection types, implicit products, and untyped equality. Now, viewers may be wondering at this point about the implications of adding those constructs to the language. Is their only purpose for yielding inductive data types in a small core theory, or are there perhaps some other interesting things that can be accomplished with them? In this video, we will answer the question in the affirmative by showing how to define terms representing zero-cost coercions between types. Doing so lays the groundwork for future videos covering such topics as generic zero-cost proof and program reuse, and generic derivations of induction for data types, as well as gives us a chance to explore some of the seemingly strange consequences of Cedille's Curry-style type theory. To begin, let's look at equality in Cedille. As mentioned previously, in Cedille, the built-in equality type is over pure untyped lambda terms. The introduction form, beta, proves that two terms are equal by reflexivity. Let's give this a go. Test refl1. Let's say that lambda xx, the untyped identity function, is equal to itself. And we will say this is true by beta. Now, reflexivity is spelled beta because it's not just syntactically equal terms, but terms that are equal modulo beta reduction. Test refl2. Here I'll show this off by saying that the identity function is equal to itself applied to itself, which is also true by reflexivity, because of course lambda xx reduces to lambda xx applied to lambda xx reduces to lambda xx. So beta proves reflexivity and beta conversion. It also proves eta convertible, that two eta convertible terms are equal to each other. Here I'll take the identity and then eta expand it. By doing that, I'll say let's abstract over another y, and then immediately apply x to y. So to summarize, beta proves that two terms are beta-eta convertible. Now I just said that Cedille is a pure type theory, which means that the terms should only be the terms of the untyped lambda calculus. But this beta axiom is obviously not a lambda term, so what gives? Well, we're writing in an annotated language which erases to the pure lambda calculus, and you can think of beta as an annotation for proving reflexivity, which itself erases to a lambda term. So if I pop open the inspect buffer, beta itself proves equality, but erases to a lambda term. So if I pop up the inspect buffer and say, what does beta reduce to? Here, you see that beta normalizes and erases to lambda xx. So for those of you familiar with Leibniz equality in the calculus of construction, the fact that the constructor of equality, beta, erases to lambda xx, should seem pretty familiar. However, I want to stress that lambda xx is not the only lambda term that beta might erase to, or indeed not the only lambda term that a witness of equality might erase to. Just the one that it erases to by default. But the subject of what the inhabitants are, what the erasures of the witnesses of an equality are, will be covered in another video. Another thing that may strike some viewers immediately is that since equality is over untyped lambda terms, and that there are non-terminating untyped terms, it should be immediate that type checking in Cedille is formally undecidable. Here's a very simple example that demonstrates this. Let's call this test omega and say that the identity function is equal to the omega term. And here we see that Cedille's type checker is spinning because it's trying to reduce this expression, which of course will never reduce. So many people might have philosophical objections to this, having a type checker that is non-terminating in general. But as a practical matter, most languages with dependent types already allow you to state types for which conversion checking can take exceedingly long, longer perhaps even than the eventual heat death of the universe, even if theoretically they are guaranteed to terminate. And just like in those languages, in practice, I found that in Cedille, you virtually never accidentally write such a term. Most of the time these comes up are explicitly examples for showing how to make the type checker loop. That is to say, somewhat artificial. Alright, well, we've covered beta, the introduction form for equality, but once we have a witness that proves equality, how do we use it? In Cedille, that's given by another primitive, row, which is mnemonic for rewrite. Row takes an equality and rewrites the expected type in a left to right fashion. So, as an example, let's prove transitivity, the transitivity property of equality. So for types A, B, and C, and for terms A, little b, and little c, if A is equal to B, and B is equal to C, we should be able to conclude that A is equal to C. As expected, the type I need to witness is A equal to C. In my context, I have the proofs that A is equal to B and B is equal to C. So I will begin by using eq1 to rewrite the expected type from A equals C to B equals C. I do that with the following syntax. Row eq1. First, you give the argument that the equality witness that you wish to rewrite by. Next, after the dash, you give the term whose type should be the expected type after rewriting. And again, for those of you following along at home, you can write row with \R. Now, so the expected type was A equals C. The type I've rewritten by is A equal B. Now, in the rest of the expression, I must prove B equals C, which of course I have by assumption. An additional convenience that Cedille provides is a symmetry operator, sigma, which allows you to take an equality and produce an equality with the left and right hand side flipped. Let's see that example in action. Test sim right? I need to prove b is equal to a. I have available that a is equal to b. I can finish by saying symmetry eq, where sigma is given by backslash little y. Symmetry is convenient, but of course not necessary, because it can be proved. The symmetry of equality can be proved with a row. Row eq beta. My expected type is a equal b. I rewrite by b is equal to a to then simply need to prove b is equal to b, which is true, by reflexivity. So sigma is not essential, but it is sometimes more convenient to be able to use than rho, which will rewrite all occurrences of the left-hand side of the equation. By default, you can also provide a motive, but with no motive given, rho rewrites by all occurrences of the equation in the expected type, which sometimes you don't want. One final use of equality that we should cover before moving on to zero-cost coercions is how you might use absurd equalities. So by that I mean that a feature that the calculus of constructions lacks, that the calculus of inductive constructions has, is the ability to prove that, for example, the Boolean true is not equal to the Boolean false. In Cedille, you can form this kind of reasoning using another primitive, delta, which says that you can prove anything from an absurd equality. So first, let's define bool, as before. Bool, of course, the encoding of Boolean is any function that takes two arguments and returns one of them. And one of these is true. And the other of these is false. And it should be apparent that even after erasure, the definitions of true and false cannot be equated. And we'd like to be able to prove that this is the case, that their equation would result, that equating these two terms would result in a contradiction. So of course, we can encode contradiction in the usual way by describing a type which is not inhabitable. Call it empty. It also could be called false or bottom. Actually, we'll call it empty. A type with no inhabitants, and then it is equal to, as expected, for all x. The type empty is a proof that all types are inhabited. So of course this should not be inhabited. We will define test absurd to be the statement that the expression showing that if true were equal to false, then the empty type would be inhabited. And we can prove this by saying delta, the type we want to inhabit, and then eq. Popping up, open the inspect buffer. Delta allows you to prove anything you want from a contradictory equation, which of course eq is. Now, we have everything we need to express the type of zero-cost coercions. We shall call these casts, and they are defined as follows. Let cast be of kind star to star to star, type constructor taking two types. We'll call these types A and B. And now a cast between A to B is an intersection, a dependent intersection between a function f from A to B and a proof that f is equal to the identity function. So let's pause for a moment to consider this definition. The first intuition that someone might reach for in defining such a type might be the following version of a cast. Similar. A dependent product between a function of type A to B and a proof that that function is equal to the identity. And actually, this intuition is totally justified. As far as our usage will be concerned in this video, cast and cast prime are logically equivalent. Cast, it turns out, is subtly more powerful, but we don't have the space to cover that in this video. But the intuition for why it is acceptable to define cast in terms of the dependent intersection rather than as a dependent product is that, as we saw before, the witness for equality, beta, can erase to the identity function. So if f is indeed equal to lambda xx, then we should be able to inhabit this intersection because f is equal to lambda xx, and the proof of this fact is also equal to lambda xx. Those two terms should share the same erasure, and therefore we should be able to inhabit this dependent intersection. Well, let's try to define a constructor for cast. Spoiler alert, our first attempt will fail, but of course it's useful to see why a naive attempt fails before showing the proper proof. So let's say draw A and B, give me an f from A to B, and give me a proof that that f is in fact equal to lambda xx. And now I should be able to form a cast from A to B. Okay. To introduce a cast, I must introduce a dependent intersection, which is, again, given by this square brackets notation. On the left-hand side, I need a function from A to B, which f is. And on the right-hand side, I need a proof that f is equal to lambda xx, which eq is. But, unfortunately, Cedille complains to us, because it is not obvious to Cedille that f and eq are, in fact, that f and eq erase to the same term. So, okay, that's reasonable enough. We have eq over here, where we it's not immediate what the erasure of eq ought to be, but we know that we can rephrase from the proof f is equal to lambda xx. We should be able to create another proof f equals lambda xx, which erases to the identity function. Let's do that. Let's say take the expected type, rewrite my eq, and then prove that lambda xx is equal to lambda xx, which is true by reflexivity. Alright, Cedille is still complaining. Now it says then it can't tell that the left-hand side and the right-hand side are equal. But while the first component remains the same, f, now the second component is lambda xx. So this should seem somewhat peculiar because we already have a proof that we already have a proof called eq that f is equal to lambda xx. And this dependent intersection requires such a proof, but unfortunately there's no, with just the tools we have now, there's no immediate way to get Cedille to see this. We need one more primitive construct, which is phi. Phi corresponds, to those of you familiar with New Perl, to the direct computation principle, and it states that if two terms, a and b, have been proven to be intentionally equal, we should be able to use this fact to introduce a term that has the same type as a, but erases to b. To make this a bit more clear, let's define a function which is equivalent to phi, that which will require us to provide a type signature to sort of help clarify the situation. So the construct, spelled phi over here, the construct phi says for any two types, a and b. Note that it's important that over here b is erased. We're quantifying over it implicitly with for all. So give me a relevant term A of type big A, and an irrelevant term B of type big B, and give me a proof that B is equal to A, and give this proof irrelevantly, and I will be able to return a B. From the type signature alone, just looking at what is relevant and what is erased, phi only takes relevantly, this function form of phi only takes relevantly a term A of type big A. The other argument B and the equality are given irrelevantly. So the only way we could possibly inhabit this is if we could somehow convert an A to a B. All right, we now must provide a B, and the only thing that we have computationally relevantly is A, so we will invoke phi. The construct phi has three subexpressions. The first subexpression is a proof that the second and third subexpression are equal to each other. Here, of course, that is indicated by whole equals whole, because we have left holes for the second and third subexpression. The second subexpression must be a term whose type we're trying to inhabit. Here, the expected type of this entire expression is B. So the term, I must provide a term here whose type is B. But crucially, I can use irrelevant terms in this position because what phi erases to is the third term. So I provide a B over here, and then my A for which that B is equal to. Let's make this a little bit more clear. I will say I will compute directly with eq. Eq says that B is equal to A, so I must now provide some big B, some term of type big B, which is equal to little b. That, of course, I can do because that's simply little b. The third sub-expression that I must provide is the thing that little b is equal to, and also what I want the entire expression to erase to. Here, little b is equal to a, and I want the expression to erase to a. What is the erasure of the entire expression? Lambda a, the identity function. This is exactly what we need to be able to write a proper constructor of a cast. Let's give this another go. Intro cast. As before, the first argument, the first component of the dependent intersection is f. Now I need a proof that f is equal to lambda xx that indeed erases to f. So that I can give with phi. I know already that what I need is for this right-hand side, the second component of the intersection, to erase to f. So I will just give f as the thing that I want my phi expression to erase to. Now I need to prove that the second sub-expression, here not yet given, is equal to f. What I have in my context is a proof that f is equal to lambda xx. So what I will say is I will use symmetry on eq to turn this into a proof that lambda xx is equal to f. Now, for the second sub-expression, I need a proof that f is equal to lambda xx, which erases to f, or which erases to lambda xx. But of course, we were already able to show this. And so, with phi, we're able to introduce our zero-cost coercions cast. Now, phi brings with it a lot of power, perhaps more than what you might expect. In particular, you might think that by the definition of intro cast, that the only kinds of casts that you can make use of are those formed by functions f that are already intrinsically equal to the identity function. However, phi can go a bit further and allow you to introduce casts with extensional identities. That is to say, while the f we might be interested in might not literally erase to the identity function lambda xx, if at a certain type it behaves extensionally like identity, such as a proof saying that for all a, f of a is equal to a, then we can use this to create a cast function that is intentionally the identity. To make this more clear, let's define our other introduction form for casts. Intro cast extensional, whose type is for all a, b, give me an f from a to b, and give me a proof that for any a I care about, f of a is equal to a. Then from this, I have enough to be able to form a cast, which again, by the definition of casts, it must be formed by a function that is intentionally equal to the identity. Again, in order to introduce a cast, I must use the introduction form for dependent intersections. Here, since we have already said that f may not be intrinsically equal to the identity function, only extrinsically, at type A, we are not able to provide f directly. Instead, we will provide a function defined using phi as follows. Lambda x, phi, extx, f of x, x. Again, to read phi, we must provide a proof that the two other terms that are given to it are equal. Here, the first term is f of x, the second term is x. The first term that we must give to it, f of x, must have the type that we are trying to compute for this entire expression. Here, since we are trying to form a function from a to b, the body of the function must have type b, and that is the very type that f of x has. The second term that we give is the term that we expect the entire phi expression to erase to. We want this entire expression to erase to lambda xx. So the body of the function we wish to erase to just x. And now, since this entire expression in the left-hand side of the intersection is the identity function, and over here, we must now give a proof that lambda xx is equal to lambda xx, which of course is simple enough to do. So we have our introduction rules for casts, our zero-cost coercions. We now ask how we can use them. What are the elimination rules for a cast? Remember that what we're trying to achieve here is a way to use casts so that our conversion from one type A to type B has zero runtime cost. Therefore, we expect the elimination rule for casts to erase to the identity. Let's try to define a first pass of the elimination rule that will fail to have this property, that will not erase to the identity, and see how we can repair it so that it has the expected runtime behavior. To eliminate a cast, I will say for all A and B, if you give me an A and a cast from A to B, then I can produce a B. So the naive first attempt at implementing this function would be to note that we have a cast in context, and the first component of that cast is a function, f of type A to B. So we project this function out and apply it to our argument of type A. But as stated, if we ask what the erasure of this expression is, we see that all we've done is implemented a form of reversed application. We take an argument A in a function C and apply C to A. And even though we know, morally, that C must erase to an identity function, and therefore the resulting expression, body of the resulting expression should just be A, this is not immediately obvious. So how can we repair this? Well, the first discrepancy we will note is that if elim cast should erase to the identity function, then it can only take a single explicit relevant argument. Therefore, this cast will have to be given implicitly. This hollow arrow is the notation used for non-dependent implicit function types in Cedille. Now we see we have a function that, even though it abstracts over 4 arguments, only one of these is given explicitly. And now the goal is to give a body which erases to A. So of course, because C is given implicitly, we cannot simply use the same definition that we had above. Because now Cedille complains that we violated its occurrence checker. Namely, that even though C is implicitly bound, it is used explicitly in the erasure of the function. Well, what can we do here? Again, we appeal to our direct computational principle phi. We know that we want the body of the phi expression to erase to A, because we want a lim cast to erase to lambda A. So we know how to fill in the first hole. We also know that the expression that we're trying to give has to have type B. So as the first term argument, that is the first non-equational argument, we have to give an expression whose type is B. And crucially, we are allowed to use both explicit and implicitly bound variables in the expression that we must give here. So in particular, we can say, use our f, our identity function, the first component of our cast, the identity function, and apply it to A. And this, of course, has type B. Finally, the equation that we must give is that the first term component, C of A, again, this should, before erasure, say C.1 applied to A, but due to the erasure semantics of intersection types, C.1 erases to C, and what Cedille presents us with is C applied to A. But anyway, we must show that C of A is equal to A. Our cast, C, lets us know that the first component, C.1, is equal to the identity function. So let us make use of that. Say rewrite by the equality given in the second component of the cast. And now ask what our expected equality type ought to be. We must now show that lambda xx applied to A is equal to A. And of course, that's true by simple beta reduction. And now we can state the following theorem. And it's true by simple beta reduction that our elimination principle for casts indeed erases to the identity function. To conclude this video, let's see our cast in action. Let's define our simple church-encoded lists and church-encoded length indexed lists, show how to perform a cast from the length index version, typically called vectors, to the non-indexed version, and how we can perform some small proof reuse in the definition of length on both vectors and lists. So first, of course, we give the definitions for a list and vector. I could give the full inductive developments defining types that for lists and vector, which admit an induction principle, but for the sake of brevity, I'm going to leave that out in this video, and instead use the simple calculus of constructions versions. The church encoding for list is parameterized by type of elements and states that for all x, if you give me an x for the nil case and an a and a function that produces from an a and an x for the cons case, then I can produce an x. The type of vector is similar, except it's additionally indexed by a natural number for the length. For all x, now x must have the same kind as the index sort of the type we're defining. So x has kind nanda star. If you give me an x over 0 and a function that for all implicit nats, if you give me an element and the tail of the list, I can produce a list. Or rather, given an element and an x of n, then I can produce an x of successor n. Then I can produce a x over n. Oh, yes, of course. Now, we can also define the simple constructors for list. Nil, the empty list, has type lambda x, in lambda c, in. Right? I need for all a list of a, so given an a, I must now produce a list of a, which of course is defined over here. So for all x, give me something to do in the nil case and something to do in the cons case, and I can produce a list here. Since I'm trying to produce the empty list, I will produce the thing to do in the nil case. The typical church constructor way of defining, church encoding way of defining constructors. Cons looks as follows. Give me an a and a list of a, and I can produce a list of a. All right, I have my church encoded lists. Now I can define a cast between lists and vectors. Note that I have not defined the church encoded constructors for vector, as they won't be needed. So what we want to say is for every element type A, for all n of type nat, I have a cast from vector, a vector of A of length n to just a regular non-indexed list. The proof that we'll give is going to be straightforward. It'll just be by beta equality. Actually, let's use our constructors here. So I need to give a proof that for all A of type vec A of length n, that the function that I'm about to give, which has not been defined, when applied to A is equal to the identity function. And here this will end up being as straightforward as just by beta reduction. Over here, I need to have it provide a function from vectors to lists. Okay. Let's reformat this a little bit so that it's a little bit easier to read. To produce a list, I'll abstract over the abstract result type. Now I need to produce X. I can do that by eliminating my vector automotive, which ignores its natural number index and instead just produces X. Here I can just provide in, and here I can provide an unused natural number argument. And provide the abstract cons constructor of the list to the two arguments A and tail. So now I have cast between vectors and lists over the same element type and for any length vector n. Now we know how to form a cast. Let's see how we might use it. So a typical use case for zero cost coercions is to be able to reuse definitions defined on one type at another type. The definition that we have in mind here will be something simple enough, computing the length of a list. Computing the length means that I'm going to use iteration with my church encoded list. In the nil case, the length of nil is 0. In the step case, actually perhaps tail is fine here. TL, tail, represents the length of the tail, and I'm going to say that the length of this list, if it is a cons, if it was formed by cons, then its length is the successor of the length of its tail. And now we can define a function computing the length of vectors. Give me a vector, and I'll produce a natural number. Note here that I can't simply just return the index to the vector because it is quantified over implicitly. Of course, I could provide it explicitly, but that would defeat the purpose of that would have some additional runtime costs carrying around the vector length. So I want to reuse my length. And I need to provide it a list. I can produce this list by using my cast. make Cedille a little bit happier by providing some additional type annotations here. The first argument I need to give is a vector, because I'm going to be computing cast from the vector, from a vector to a list. And the second argument I need to provide is indeed the cast that shows that vectors can be zero cost converted to lists. Right. This annotation is no longer necessary. So as you can see, in this case, the definition where we reused the function length to define length over vectors ended up being longer than if we had written it directly. However, you can imagine in a less for a less trivial definition, a less trivial function, that it would be pretty useful to reuse the definition of length, reuse the definition of the function that you care about over a different kind of data. And importantly, the property, another important property that we want to have, because these are zero cost coercions, that length should be equal to b length. And this, again, holds by beta reduction. This concludes this video on Cedille, on equality and zero cost coercions. I hope you enjoyed it. The next video will be a proof of Tarski's fixed point theorem, which you can use in Cedille to define recursive types. Crucially, that development relies on the machinery for casts we saw here. Hope to see you then.